Good afternoon. We have a fun topic to talk about today. In fact, two. I will be talking about discounting first, and then Carolyn will be talking about the green paradox at 4. And so I've been working off and on this topic for quite a long time. And so this is joint work with Christian Azar, for instance, with Michael Howell, with Martin Persson, with Olof Johansson Stenman, Christian Gollier, and then the science paper has like a dozen people, including Arrow. So that's something to be proud of. He is fantastic, by the way. So we have that's another paper, and a few days ago the final proofs were sent around. Arrow he must be about 93 now, and within 10 minutes, like, reference 2 is missing. Like the footnote somewhere. It's pretty incredible. So you might sort of wonder what discounting has to do with policy instrument design, but I think it has a lot. Discounting is about how to value the future, and we need to figure out those values in order to decide what level to put our policy instruments. So that's one obvious use. In the United States now, for instance, we have a battle. This is a big battle with lots of sharp pens and lots of millions of dollars being spent fighting for the social cost of carbon. Some of us want to raise the social cost of carbon, or we want to get the correct number. And some people want to get rid of the social cost of carbon, right? And basically not have this number. Now the Department of Energy, Department of Transport, and other departments, they are forced to count and consider the social cost of carbon. And the social cost of carbon will be much higher if the discount rate is low. So therefore the discount rate is very important. And anyway, it's a fascinating topic. This is the value of the future, in some sense, a price on the future, as close as you can get. The first time that I can remember that I started thinking about discounting was when we were talking about nuclear waste, and we had a big debate on nuclear power in Sweden. If you're going to build a power station, or you might have different technologies, either a nuclear power station or 1,000 windmills or something, then you know the benefits. Basically, that's the value of electricity. And the costs, there's a cost of building the plant, and in the case of nuclear plants, there's some fuel, and there's some labor. And then when it comes to nuclear power, there is a big waste problem afterwards. But later, right? So it's in the future. And I remember once there was a study that showed that somehow the problem of taking care of nuclear waste was twice as bad as we thought. So this kind of calculation sort of seemed to show then that nuclear was not such a good option. But the people, my opponents, I was debating this at the time, they said, it doesn't matter. We'll build the nuclear storage site in 2060 instead of 2050, and then we can use the same numbers. Because if you have 7% discount rate, and you delay something by 10 years, the cost falls to half. So I thought, that's cheating. I felt cheated. I thought, this discounting business, that seems like cheating. So, that's what they did. And the funny thing about nuclear power, actually, a little funny detail, is nuclear power is really expensive and uneconomic if you have a low discount rate, if you have like 1% or something, because then the waste costs are enormous. If you have a very high discount rate, like 10% or something, then the building of the plant becomes a problem. So you can solve for the optimal discount rate if you really want to promote nuclear power, and there are people who do that, for for a living. You can find the optimum discount rate. It's about 3%. Will make nuclear power look fairly good. So there was a public inquiry at some time in the 1970s that decided that Sweden should have a discount rate of 3%. And I felt that that was maybe designed to specifically help nuclear power, which I don't know. Anyway, could someone lend me a piece of paper? I need a piece of paper. This is a children's kind of trick. Oh, don't think, yeah, you won't get it back, right? So, you know how thick this is? It's about 1/10 of a millimeter. So if I now double the size of the pile, I could just fold it, or I could tear it. Now I've done that once. That's 2 times, 3 times. Now suppose I did this 40 times. How thick would the pile of paper be? It would be that was 4 times, I think. So if I did 40 times, how do you think the pile would reach me to here, or to here, or to the size of the building, or how far would the pile of paper go? You can guess.
It will reach the moon.
It will reach the moon. That's fantastic. You could give the lecture instead. So, because it goes 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024. Right. 2048, 4096, and so on and so on. But basically, you get to 1,000 after you've done 10 times. 1,000 times as thick. And then, of course, if you do 20, it would be 1,000,000. 30, it would be 1,000,000,000, and 40 is whatever they call it, like 1,000,000,000,000. And that's, if each piece of paper is 1/10 of a millimeter, that's 10 to the minus 4 meters. Then you will get 10 to the 8 meters as 100,000 kilometers. It's actually 384,000 kilometers to the moon. But then on the other hand, this is actually wrong. It's actually 2 times 10. So you almost, maybe you have to do it 41 times to get to the moon. It's still quite impressive, isn't it? And this is a simple way of saying that when you raise things to the power of something, numbers get very big. So that's kind of the fundamental mathematical principle you need to remember, because that is the principle of growth and of discounting. Right? If we have, oh, do you know this, by the way? So if we have 7% growth, how long does it take before we double the size of the economy? 10 years? How did you know that? And if we have 3%?
24.
And the principle is, if you have n, or r I suppose is a better, then you have 72 divided by r. And I suggest you try to prove that at home. It's not very difficult. Think about the logarithm of 2, and you'll find it out quite quickly. Or you can Google it. Just to say though that if you have 7% growth, or you could have 10% growth, like they have in China, then the economy doubles in 7 years. Now, you saw what happens when things double 40 times, right? So suppose you had 10% growth for 280 years. Why 280? Well, it doubles in 7 years. So if you do that for 280 years, you'd have 40 doublings. and the Chinese economy would grow from a thin piece of paper to all the way to the moon. Right? You think China can get 10 to the power 12 times richer than it is today? What are they going to eat? I mean, you know.
There's a limit, right?
Well, that's one of the questions we're going to talk about today, if there are limits or not. And another question is the one you already raised. What's the relationship between growth and discounting? But just to sort of talk about the relevance of this subject, the Stern Review said that, you know, climate change is the biggest externality man has faced. The size of the problem might be something of the order of 5 to 20% of future GDP. And that it could be more because there are enormous uncertainties. And there's uncertainties like cloud formation and methane and ice melting and guess which is the biggest uncertainty? It's the discount rate. The discount rate dominates all these things. Just makes such a big difference. And the conventional idea is of discounting, you have a cost or a benefit sometime in the future with the value v, and then we say that today the value is 1 plus r to the power minus t times v. So if you have a cost of, say, $1 billion, it could be, of course, thousands of billions. No, the drowning of Bangladesh. It's rather hard to value, first of all, but suppose you have a cost of $1 billion in 400 years. That would be worth $3 today, right? I just got that in an envelope. Someone sent me, I don't even know why, a friend. We had dinner the other day and then he sends me 20 kroner. I don't know why, and it really doesn't matter, right? Okay, because this isn't very much money. $1 billion in 400 years, right? That's, you know. Now, suppose it had been $1 billion in 500 years, that would be, what's that, 2 cents? I don't have that little money. I mean, we got rid of those coins in Sweden. So there is nothing that small. If it had been 6% instead of 5%, it would have been 0.02 cents. So the difference between 5% and 6%, how much is the difference between 5 and 6?
1.
Yeah. Or you could say it's 20% difference. But then you see the difference is a factor 100 here. So, good advice, if when you're working with discounting, take a deep breath, sit down, remember this is multiplication and exponents. It's not adding things. So that the math quickly gets out of control. You've got to make sure you do it right. And because people say, well, okay, right, we don't quite know the discount rate. Maybe it's 5 or 6%. Yeah, but 5 or 6% makes a very big difference. We have to know if it's 5 or if it's 6, and we really don't. Right? That's one of our problems here. That's why discounting is a bigger uncertainty than the cloud formation or whatever else. Because even between 5 and 6% is a difference of 100. Between 1% and 10%, it's I don't know what it is, but it's a gigantic difference. This could be wrong in one or two ways. So, you know, maybe there are other uncertainties that are equally big, and maybe in some calculations, it depends. I mean, we're going to get deeper into this as the day goes. And if, for instance, I was assuming we have a fixed cost VT that we're going to discount. Then the discount factor makes a big difference. It would be slightly different if we know that we are going to lose a certain percentage of GDP. Then the calculation becomes different, but so, yeah. Still, the discount factor is important. I guess that's what I wanted to show. And of course, now I want to sort of persuade you that growth and discounting are just two sides of the same thing. Think of $1 in the bank today, it will be $2 in 6 years' time if there's 12% interest rate. So you can say that $2 in 6 years' time is the same as $1 today. So that's growth on the one hand and discounting on the other. You can draw this easily, of course. This is what happens in 24 years, you get 16 times bigger. In 60 years, you get 1,000 times bigger. And then 240 years, you get this like billions, hundreds of billions times bigger. That kind of seems to suggest that countries can't grow for several centuries. So maybe that's worth remembering. This is impossible. And remember that, because I will get back to that. Right? So, growth is 1 plus r to the power t, and discounting is 1 plus r to the power minus t, or in continuous time you have e to the power rt and e to the power minus rt. They are just mirror images. Well, we have lots of sort of aspects of this. One is, can growth go on forever? Question mark. Even if growth can go on forever, maybe our brains don't think that way. And there have been experiments with both people and animals. And you know, if you get a bar of candy now, or you get it in tomorrow, which do you, well, how strong is your preference? We all prefer it today, basically. But how strong is that preference? And then maybe that's not the same. You could also ask the question, you're going to get a bar of candy in a year, or in a year plus 1 day. And then people say, that doesn't matter. But it's still the same day's difference. So we have all kinds of mental discounting. Then risk comes in, and uncertainty comes in, and relative prices I'm going to talk about, one of my favorite topics. And I'll start with relative prices. Well, yeah, start with relative prices. Because basically, we can complicate this a little bit. We can say, okay, that's the value of a project in the future, but maybe, suppose this is the drowning of a piece of land somewhere, but maybe the relative price of that land will change over time. Well, then the value becomes this, and you can see that if P and R happen to be the same size, then there really wouldn't be much discounting. So relative prices potentially could be important. And I'm kind of proud of this. This is kind of my idea. So it's one of the few things that I can say is mine in economics. I'm going to take the example of land, and I checked what the price of land, how fast it's been rising the last 50 years in London, and it's like 19% per year, and in Scotland it's just 11% per year. So if you inherited some land in the centre of London, you're rich. Yeah. Well, that's what the Queen and a few other people, the Duke of Westminster and a few other people are doing. They're holding on to that land. You could also say this means that when London gets flooded by climate change, that's going to be expensive. So of course they will put up walls. London may be protected ultimately. I don't know. I mean, there's a big river going through, so that makes it complicated. 100 years ago, about 10% of the population here in Gothenburg had a maid. You know what a maid is? Yeah, they're very useful. They kind of help clean the house and make food and stuff. Yeah. And the incomes have been growing by 5% per year. So the question is now, how many percent have maids now? We all got a lot richer. And the big question is, when do we all have a maid? When does 100% of the population have a maid? Yeah, and why doesn't it work?
It's expensive to pay that.
Yeah, the relative price of maids is going up roughly at the same rate as income is. So we don't get more maids. That's another thing I've been thinking about. You see old houses in Sweden, they're made of wood, and the carpentry is very nice. So there's lots of little details. And those houses are a pain, because you paint them often, and you need a really expensive carpenter and painter, and it takes a lot of time and money. And we can hardly afford the upkeep of those houses. And then I think, how could they afford to build them 100 years ago when the country was much poorer? But then again, the price of labor has changed, like income has. So a lot of prices change in the economy. And we also checked how much the world, how much food is a percentage of GDP. And it seems it's about 24% of GDP. So this is actually a calculation kind of to do with climate. Suppose you lose 1% of agriculture because of climate change. How big is the loss? Well, it's roughly 1% times 24%, so it's like 1/4%. You with me? Mm-hmm. Now suppose we lose 95% of world agriculture. That would seem to be 23% of GDP. And we sort of all feel, well, there's something wrong here. What is wrong with that calculation? Relative prices, exactly. The price of food would be so damn high that you'd have to pay 100 Kalashnikovs to get 1 carrot, and only the very richest people would be grabbing the food that is left, right? So the 5% of the food that is left would actually be so valuable that it would rise so fast it would become the whole of GDP almost. You know. There are lots of things. The first article about this that I wrote with Michael Hoel, who is a fantastically clever Norwegian economist, and we were in Oslo writing this, and there was no snow. He's also a very good skier. He skis faster uphill than I ski downhill, and so we were writing about this. There's not going to be enough snow for skiing in the future. This is really, the price of snow will go up. But there's also lots of other things, right? Biodiversity, wildlife, and so on. Lots of things that will become scarce, and their values will change. The coral reefs, with all their beauty and all their fish, are threatened and will disappear. So that was kind of the anecdotes. I like anecdotes, as you noticed, but we've got to do some formal economics as well. So why do we discount? What are the reasons for discounting? You have any suggestions? For comparison, yes, that's right, but I'm not going to write it. down. I mean, that is the overall reason. But why would, so what kind of reasons? Preferences, yeah. What's going to happen in the future? We will be richer, we think. Yeah, well, we hope. Richer or well, growth, maybe I should write, right?
Uncertainty?
Yes, uncertainty is a very important one. Suppose you eat dinner with Rockefeller, and then there's a discussion of, who's going to pay the bill. It's kind of better Rockefeller pays the bill, because it really won't make any difference. He will have just as much money left after he's paid the bill as he had before. It doesn't make any difference. Whereas to our income, it would make a difference. So people who are richer, if you have someone who is very rich and someone who is very poor, it's better that the rich person picks up the bill. So if we think that our grandchildren are going to be richer than us, then those rich little brats, they can pay the costs. And then we should not be, saving now to help them. We should be enjoying ourselves now. We can leave the problems to them. They will have such fantastic technology that their robots will take care of whatever problems we leave, basically. That's the idea of, one of the reasons for discounting. There's one more, which is related to preferences, and it's our preference for impatience. This is like the question of whether you want the ice cream now or later. It's always now. We just prefer things now, and we're selfish. So the two arguments, right? The income and the discounting. People who we will be richer and we are impatient, and then rich people don't know the value of money. And I'm going to formalize that a little bit, and we have this formula. We define welfare as the integral into the future of utility. Utility in any particular moment depends on consumption at that moment, C of T. But we also have this, here we have something we call pure time discounting. This is to do with impatience. Pure time discounting. Sometimes called utility discounting also. So we're integrating over utility, maybe in fact even until eternity, if we believe in eternity, of utilities, but somehow we don't count utility 500 years from now quite as much as now because of this pure time preference. So one question is, how much should this impatience be? And there's a lot of philosophers, including some important economists and moral philosophers like Rawls, who have said that this should be zero. That rho should be zero. There is no moral argument for this utility discounting. That people in the 500 generations away, or 500 years away, their utility is worth just as much as ours. One of the clearest arguments against that and for a positive rho is that the world might be destroyed for some exogenous reason, that is not by us or by global climate change, but by a big enough meteor, for instance, or something like that. If a big enough meteor is going to hit the Earth with a probability, delta, then it would be a pity to do a lot of saving for the future after that time, right? So But that's an argument for a very small rho, because we know the Earth's been here for a few million years, and we haven't been hit by a meteor yet big enough to destroy the whole Earth. So this doesn't happen very often. So that's a reason for a very small, but there would be some small, maybe just a thousandth of a percent or whatever it would be, some small value. Otherwise, of course, you could say, well, I'm selfish, what's the future ever done for me? I think that's a line by Andy Warhol or someone, or some comedian, I've forgotten who. So you can be selfish, you can choose a bigger rho, but if you're being moral, you choose a very small rho. And some people argue for 0. But there is still a reason for discounting in the growth. So the whole point of discounting is to see how the marginal value of consumption changes over time. Okay? How the marginal value of C changes over time. So what is that? Well, the marginal value of consumption is dW dC. And we want to see how that changes over time. Well, that is that. Right? And we typically normalize it by dividing it by itself, so to speak. So this is the relative rate of change of the marginal value of consumption. So that's what we call discounting, the discount factor. Now all we have to do is just a simple mechanical derivations. Okay? So I'll write it as W prime, okay, dW dC. Here, that will be minus rho times all this, basically. Plus then I want to take a derivative of this term, and then I'm going to get e to the minus rho t times u prime, that is du dc, times the internal derivative, which is dc dt. And then I wanted to divide all this by, let's see, that's just w prime so far. Then I need to take the time derivative of this. Yeah, so that was w prime. Now we want dw prime dt. So the time derivative of this, no, I made a mistake somewhere, didn't I? Yes, I did two things at once. You were all nodding instead of correcting me. I kind of did two things at once. There we are. That is w prime. dw dc. Now I'm going to take the derivative with time of this with respect to time. Now I get this minus rho times e to the minus rho t u prime. See? Plus this e to, now first I derive this and multiply by this. Then I take this and differentiate this. So plus e to the power minus rho t times the second derivative of u times the internal derivative dc dt. So that's this part here. It goes away nicely enough. No, I don't think so. I think this is a series of value, and when I take a derivative with respect to one particular t, I just get that one. So I'm differentiating this with respect to c. This goes away because it's just one moment of time I'm looking at. This is still there, so it's just unaffected because it's not a function of c. And this is the thing I differentiate with respect to ct, because I'm differentiating dw dc. So I get u prime du dc. Right. This is du dc here. Then the second time round, when I differentiate this, I differentiate this, because now I'm differentiating with respect to t, the second time. The first time with respect to c, right? Now I'm differentiating with respect to t, therefore this thing first needs to be differentiated. You think of the chain rule here, or whatever it's called. So you do this one first, minus rho to the power e minus 3, just multiply by this. And then you take plus this thing, and then you differentiate this one, and you get the second derivative of u times the internal derivative dc dt. No, you have to do both, because you can, well, I mean, think of this as a sloppy, this is a limit of a number of a sort of a sum of different e minus rho t u c t, and then plus u c of t plus 1, and u c t of plus 2. And so it's just, there's a whole series of u of c of t minus 1 and t minus 2 and t, and then it's just that one that is affected, all the others go away. So that gets rid of this thing. And then, but then we still have to take the partial derivative, because we're differentiating with respect to not to u of ct, but we're differentiating with respect to c of t. So it's an internal derivative. So there. It's a good idea to go through this on your own. It's the kind of thing you want to be able to do when you're out to dinner, maybe, talking to your boyfriends and mothers and so on, what did you do today? Oh, we, and then you just go through it and make sure you know it by heart. Okay, so this was dw, the time derivative of the marginal value of welfare, right? And then I wanted to divide that by w prime, which is this. So I get all this divided by e to the minus rho t u prime. And you see, nicely, lots of things go away. This goes away, and we're left with rho. And here, this goes away, and we are left with u prime, u bis divided by u prime, sort of what we have here. We can do this also very nicely for, you can write it more formally. We call, there's, it's, I don't want to do too many derivations on the table, but it's quite easy to show that this times dc dt divided by c, this is the marginal utility of the elasticity of the marginal utility of income. And so we often call that eta. And so this formula simplifies into this nice formula over there, minus rho plus eta times g, where g is dc dt divided by c. This divided by c And this is that C that comes into the definition of the elasticity of marginal utility. We can also do this. There is one utility function, one family of utility functions that is very popular. That's called the constant, what do they call? Yeah. It's not constant elasticity of substitution, it's constant elasticity, marginal, I've forgotten, anyway. But anyway, that is written like this, C to the 1 minus alpha divided by 1 minus alpha. And the nice thing about this is you see the marginal utility, take the derivative of this, it's just C to the minus alpha. Because you get 1 minus alpha here, that goes away. The second derivative of the utility function is minus alpha C to the minus alpha minus 1. For instance, you can calculate here the eta is equal to minus u double prime divided by u prime times c, and that is equal to alpha c to the minus alpha minus 1 times c divided by c to the minus alpha, and all that is just equal to alpha. So another way of writing the so-called Ramsey formula is this. And there basically you have these three reasons. You have impatience, rho. That is one reason for discounting. We just don't care about the future. And then we have growth. People are going to be richer. That is G. And then rich people don't know the value of money. That is the marginal elasticity of utility. So that's kind of also an aspect of our preferences, if you like. Rich people don't understand how important money is. They don't care so much about money. The marginal elasticity of utility with respect to income goes down. As you get richer, $1 more or less just doesn't matter very much. That is, basically the concavity of the utility function. We think of consumption as you get richer, and utility, we think it looks something like that. So more consumption is always good, but at a decreasing rate. So if this is U, then this is U prime. That's what we think about the utility function. We don't know the exact shapes, but we kind of know something about the shape. Now, the good news, guys, is that this is the very simple story. It's now going to get a lot more complicated.
And that is good news?
Well, if you want to write articles. Oh, so this is still the simple concept. Suppose we think that impatience is, does that mean everybody needs a break or what?